to everyone, both live and also virtual, wherever you are. We want to thank you, the friends today in the park, for this important discussion. And we'll go over various panelists today. And then also, if you have any questions at the end that are more than their time allotment, feel free to email us and we'll get them to the scientists. So thank you. A little bit about the Friends, and I don't want to take up too much time, but we're a CSO and we've been in existence since '95, so over 25 years. And we'd like it, if you have an opportunity, take a look at our website and join as a member. Thank you very much. Right now, I'm going to introduce Emma.
Yeah, we'll introduce ourselves. No worries.
Ignazuski. Okay.
Yeah.
Thank
okay.
you.
That's
Thank
great.
you.
Hi, everybody. Thanks for coming out. Good to be here with all of you. And my name's Nathaniel. I'm batting first here for Climate Up Close. And I'll let, okay, next up, please. I'll let the other scientists introduce themselves as they come up, but I'm a PhD student at UC Berkeley, and I'm initially from Philadelphia, and this is actually my first time in the area, first time in Florida. It's been great to be here, and I'm looking forward to checking out Wakulla Springs after our talk. And I'm here on behalf of Climate Close, so let me tell you a little bit about us, about who we are and who we're not. So just to be clear right off the bat, there's no corporate money behind us. We're not affiliated with any political parties. We don't take any government funding. We're really just a ragtag band of climate scientists who volunteer their time because we're passionate about communicating the science. And the roots of the organization go back a couple of years to this sense that there's a national conversation happening on climate change right now. In the media, in our homes, in our places of worship. And in many important regards, that conversation feels out of touch with the scientific dialogue we're having in our laboratories and in our research groups. And because climate change feels like such an important issue, because it feels like one of the defining questions put to our generation, what are we going to choose to do about climate change or not do about climate change? We felt really compelled to get out there and to help bridge that gap through direct face-to-face conversations between the public at large and between scientists like ourselves. And that's really been a two-way street. We found it phenomenally productive on our end to be forced to look at the big picture and to have the public guide us towards what the right questions are to ask. And even from a research sense, you know, I'm going to give this presentation, but afterwards we're going to have hopefully an extended question and answer session and conversation that will spill out of it. And that's led directly to research projects and papers that have really been stimulated by the public's curiosity. So I know I'm going to get something out of this presentation, and I hope you will too. I've touched on this idea of, well, let me briefly say that we're mainly from the Northeast, and so that's where we've done our past outreach. And we're fortunate enough to be hosted here by Jenny Odom, and we're stationed in Apalachicola. So we're going to be doing a couple events around the area. And I've kind of hinted at this national conversation. And to start off, I think it can be helpful just to get a sense of the real diversity of voices out there communicating about climate change. So I'm going to go through 3 quotes, which I think represent different camps. And for each one, I'd like you to take a moment, reflect on how it connects with your own personal view on climate change. All right, so this first one is, scientists continue to disagree about the degree and extent of global warming and its connections to the actions of mankind. And that was said by former head of the EPA, Scott Pruitt. All right, here's a contrasting view. It probably makes no difference how badly we overshoot 2 degrees Celsius, or roughly 4 degrees Fahrenheit. Once the point of no return is passed, the world will become self-transforming. So obviously a contrasting viewpoint. And this was expressed by Jonathan Franzen, writing in the New Yorker. And the last quote here is probably on a topic that's near and dear to you here as Floridians. And that was, let us be clear, Hurricane Dorian has everything to do with climate change. And that's a quote by Senator Bernie Sanders. Okay, so maybe some of these quotes resonated with you, maybe other ones you thought were far from the mark. But what might surprise you is that as climate scientists, we actually wouldn't fully endorse any three of these. In fact, each one contains at least one kernel of misunderstanding about the science. And so our goal today is to really bring through those quotes and through explaining the science, really make crystal clear what exactly is the boundary between what's settled, what we know and take as givens and facts in climate science, and what's uncertain, what's potentially media spin that you're encountering in all of these conflicting messages. And so to get that process started, I'm going to welcome up our next scientist who will be joining us virtually, Katie Latimer, to tell you about some of the, is your audio on, Katie, just to check?
Yeah.
Okay, great. So Katie's going to get that started.
Cool. Thanks, Nathaniel. And this is a picture of one of my favorite hiking trails in the East Bay area, where I've been a student for the past several years in the physics department at UC Berkeley. And to start us off, I want to try and hone in on exactly what it is that we're going to be talking about together during our time here. Because a lot of times when we hear the word climate in the mainstream media, that is used as this umbrella term to encompass a lot of different phenomena. And so I want to distinguish between local environmental change, like the construction of big cities, the damming of rivers, or production of really huge quantities of food and garbage on a day-to-day basis, from what we're going to be talking about today, which is global climate change. And that's not to de-emphasize the importance of local environmental change, but in the limited time that we have for today, we're trying to zoom out and ask what are some really universal changes that humans have had on the planet Earth that affect everybody, no matter who they are or where they're living. And when we zoom out like this and look at really large distance and time scales, one of the most important factors that we see that humans have contributed to is the levels of carbon dioxide, or CO2, that are in our atmosphere. And this graph is showing a timeline of those levels of CO2 in the atmosphere, which stretch back to around the 1950s, when climate scientists started to figure out ways of measuring CO2 concentration really precisely. But if we zoom back to the mid-1800s and measure the difference between what CO2 levels were back then versus what they are now, we see that there's been an increase by about 50%. So that's pretty significant. And it also matches with what we know in terms of how much fossil fuels humans have burnt over our history as a species, especially after we started large-scale industrial activities, as well as different ways that we've changed the how we use the land. Another trend that we can measure over the exact same time period is an increase in the average temperature of the planet Earth. And so since the year 1850 up to the present, on average, the temperature has increased by about 2 degrees Fahrenheit. So these are two trends that we know just purely based on observing what's going on around us. And if we want to go a step further as scientists, not just say, okay, what do we know from observations, but actually try to explain those observations, we can get a pretty good start just based on our fundamental understanding of the physics of different molecules, especially carbon dioxide, because scientists have known since about the 1850s that carbon dioxide is really good at trapping heat and radiating it back to where it came from. So we could hypothesize that if we add more CO2 to the atmosphere, there will be more of these molecules that are able to stop the heat that's radiated out from the surface of the planet and send it right back down again. And this is an effect that has been called the greenhouse effect, an analogy to how a greenhouse keeps heat inside of the glass walls to keep the plants warm. And this is a good start, but we really want to make sure that we have more conclusive evidence to definitively say that not only are these two observational trends related, but actually that the increase in CO2 is in fact causing the increase in the temperature. And in order to nail that down a little bit more firmly, we use climate models. As scientists or mathematicians or what have you, when we talk about models, we're talking about the process of taking all of our knowledge and theories and understandings of how a certain system works, which in this case is the global climate, and condensing them into a list of mathematical equations. And some of these are shown, for example, on this slide. And even though we could write down these equations using pencil and paper, they are, in the case of the climate, way too complicated for us to solve by hand. And so what we do is we code them all up in a big fancy supercomputer and let the computer solve them for us. And then we take what the computer spits out and use that to that information to understand better how the climate works. And so we can use this type of model to run two separate experiments. One is we imagine an alternate universe where humans have not emitted all of this carbon dioxide into the atmosphere, but everything else about the planet is exactly the same. So all the same ways that our weather and climate work, as well as different ecosystem functions are the same. And when we look at this alternate universe, the temperature timeline since the middle mid 1800s doesn't show the same increase. So basically temperatures are flat except for some natural variations. But if we run the second experiment on this climate model and we include the carbon dioxide that humans have emitted over time, the resulting temperature graph over time actually matches with what we observe pretty well. And so this is the evidence that we need to conclusively say that yes, the increases in atmospheric CO2 have caused the increase in temperature. And at the end of the day, we were able to go back to this first quote that Nathaniel had shown and say pretty definitively that this quote is incorrect, that scientists don't in fact disagree about whether and how much global warming is happening, as well as its causal relationship with human activities. In fact, about 97% of people who are actively researching the climate right now do stand behind the consensus position that humans are causing climate change. And with that, I'm going to hand it over to Aaron to talk about what we see as some of the major impacts of that climate change.
Great, thank you, Katie. My name is Aaron Match. I'm from Harrisburg, Pennsylvania. This is what my front yard used to look like whenever it would snow. I'm a weather nerd turned climate scientist. I recently defended my PhD at Princeton University. I'm now a postdoc at New York University. And today I'm going to tell you about the observed impacts of climate change. How is climate change affecting things that we care about? And what I'm going to do is map those impacts in this space of climate knowledge to try to position them, what is settled, what is uncertain, try to cut through some of the confusion that can sometimes emerge with the messaging you might hear about the changes. So the first observed impact, Katie talked about, but I'll position it here in our chart. It is settled that carbon dioxide is increasing and that is causing average temperature increases. The next climate impact I'll talk about is another impact that is settled, and that is sea level rise, something that might be of great interest to people in Florida, as well as to those in New Jersey, up where I live right now. Sea level in the global average has risen by 8 inches since 1900. Where does that 8 inches come from? 3 inches out of the 8 have come from thermal expansion. So just like when you take your temperature with a thermometer, the mercury expands as it warms. Water does the same thing when it warms. And we are warming the water as a consequence of global warming, and it is expanding. And that has led to 3 inches of the 8 total of sea level rise. The other 5 inches of sea level rise have come from the melting of ice. That might be more familiar as a cause of sea level rise, the melting of ice. But I want to clarify that it's only ice that is on land that raises sea level when it melts. There is a lot of ice on Earth that is on the ocean, that is floating sea ice. The Arctic Ocean is often covered with sea ice during the winter. And when this ice melts, it actually does not raise sea level. No, that doesn't mean we don't have to care at all about melting of Arctic sea ice. For example, that's where the polar bears live. But in terms of understanding what causes sea level down here, it's not the melting of Arctic sea ice. And you can actually test for yourself the reason that melting of sea ice doesn't raise sea level. It's the same reason that an ice cube floating in water does not change the level of the water as the ice cube melts. Okay, so that was sea level rise. That is a global average effect. It's happening everywhere. It's settled science. Next, I'm going to talk about how climate change has impacted extreme weather. A lot of people think or understand that some of the greatest impacts from climate change might not come through these average changes, but through changes in the extremes. So what do we actually know about these changes in the extremes?
Sorry.
I don't know why I didn't think about that time. Thank you. So the first extreme I'll talk about is heat waves. Across the globe, heat waves have become 2 degrees Fahrenheit hotter as a consequence of global warming. This 2 degrees Fahrenheit might look familiar. That's the same amount by which the globe has warmed as a whole since pre-industrial times as a consequence of fossil fuel emissions. And this motivates us to develop a rule of thumb for understanding how climate change is affecting heat waves. We can basically understand that global warming makes heat waves worse by roughly adding the global mean warming on top of whatever temperature might have occurred otherwise. So a 90-degree day becomes a 92-degree day. A 100-degree day becomes a 102-degree day when we have 2 degrees Fahrenheit of warming. I actually went ahead and looked to see how well this rule of thumb performs here in Tallahassee, or north in Tallahassee. And there's a long-running meteorological station at the Tallahassee airport. I grabbed the temperatures from that station and I split it up into 2 periods. The first one is 1940 to 1980, when there was less global warming. And what I'm showing here is the distribution of temperatures from that station. This is the daily high temperature every day from 1940 to 1980. And the way to read this is that there were 600 days where the high temperature was exactly 90 degrees. And so this is the full distribution of temperatures in Tallahassee. And what we expect from global warming, based on this rule of thumb, is that those temperatures will shift towards the right, towards the hotter temperatures, and that it will be a shift that's relatively uniform across all of the temperatures. And I'm showing that shift. This is a prediction in magenta, a prediction for what global warming will have done to temperatures in our more recent period from 1980 to 2020. And now we can see what the actual observed temperatures were from 1980 to 2020. That's in red, and you can see that it agrees very well with the simple prediction from the rule of thumb. You just add global warming on top of what you would have had otherwise. It agrees especially well over here in this right tail of high temperatures, the heat waves that Tallahassee experiences. This rule of thumb also has implications for how to think about cold waves. So it suggests that cold waves should become hotter. They should become less cold. And that messaging has been we've seen some confusing messaging about that, especially following the Texas cold wave recently, where there were some people suggesting that cold waves might become more frequent as a consequence of global warming. But that's not what we're seeing. That's not the consensus science. So when it's really hot during a heat wave, it's often not just the heat that leads to your discomfort, it's also the humidity that leads to your discomfort. And when the atmosphere is more humid, sweating is less efficient at cooling the body. And we have seen changes in humidity. The atmosphere has gained 7% more water vapor on average as a consequence of global warming. This has implications for how we feel during heat waves, but it also has implications for the water cycle. And this is of great interest to people who want to understand how climate change is affecting rain, affecting snow, storms, and droughts. So I'm going to talk about that next. And I'm going to talk about that, I'm going to develop an analogy to help everybody interpret how climate change is affecting the water cycle. Air holds water vapor in it like a sponge holds liquid water. So what do air and a sponge have in common? So over here we have some dry air, over here we have a dry sponge. For both of them, you can add some water. I'm adding liquid water to the sponge, and I'm adding water vapor, gaseous water molecules, to the air. And you can keep adding water to both of these, but you can't do that indefinitely. Eventually, you reach a saturation point. A sponge has a saturation level where if you tried to add more water, it will just run off the sponge. And air also has a saturation level. If you try to add more water vapor, it will not stay in its gaseous form. Maybe it will condense into rain. And this saturation level can help us build some intuition for how global warming is affecting the water cycle. And the key insight is that the saturation level, or the size of the sponge, increases when you warm the air. So warmer air can hold more water vapor before becoming saturated. And that's like making the sponge bigger. So if you want to hold more water in a sponge, you had some way to make the sponge bigger, you can hold more water. And that's what global warming is doing to the water cycle. The first implication that has is that heavy precipitation has intensified by about 7% as a consequence of global warming. And the intuition I want you to think about here is the heaviest precipitation that we ever experience, that occurs when you have air that is close to its saturation level, and it is raining out as fast as the atmosphere can get it to do that. And in that case, that's like taking that sponge and wringing it out as fast as you can. And if you have a bigger sponge, then you can get more water out in a given amount of time. This is how global warming is affecting the heaviest precipitation levels. And you'll see that this heavy precipitation has intensified by roughly 7%, which is the same 7% by which the water vapor in the air has increased. This increase in heavy precipitation, we think that it is occurring on average across the globe, but we have reason to believe that it is also happening in hurricanes, a phenomenon of great interest here in Florida to understand. So hurricanes are intensely energetic. They're close to being fully saturated, and they're raining out water as fast as the atmosphere can rain it out. And so if you warm the atmosphere, then you increase how much rain you can get from a hurricane. It's important to keep in mind, though, that hurricanes are rare, and they're very hard to observe because they have a tendency to destroy any instruments that you might use to observe them. And for these reasons, we don't actually have a confident data set specifically showing how hurricane rain has increased yet. But this is something that we think is happening, which is why we wanted to share it with you today. Something that we know is happening with hurricanes, without a doubt, is that sea level rise from global warming has added to storm surge. We can think of sea level rise as just coming in on top of whatever storm surge would have occurred as a consequence of the hurricane. And if you remember, there have been 8 inches of sea level rise so far. So we can think of every hurricane storm surge as now having 8 extra inches of water. This can deepen the amount of flooding for properties that would have been flooded anyway during a hurricane, and it can also expose new properties to flooding. So I've talked to you about how we understand that climate change can exacerbate particular aspects of hurricanes. We think it should make the rainfall more intense by 7%. We see how sea level rise is adding to the storm surge. And that makes it seem like we can tell you that climate change has made hurricanes worse. And a lot of reporting suggests that we'll say exactly that. It will say that hurricanes have been worsened by climate change. But there's a hiccup there that is not often acknowledged, but we want to share with you today. And for that reason, we hesitate to say with confidence how climate change has affected hurricanes. And that's that we don't know how climate change has affected the number of hurricanes. And actually many climate models that we use to forecast the future climate, they'll often predict that we'll get fewer hurricanes in the future than we do today as a consequence of climate change. And if that were true, then we would have to conclude that climate change might actually make the impacts of hurricanes less bad. And so for that, because we don't know how climate change has affected the number of hurricanes, we are hesitant to say, to make any overall comprehensive statements about climate change making hurricanes worse. We can look at what has happened with hurricanes so far through history. We'll take all questions at the end. Thank you. We went ahead and looked at how hurricanes have changed throughout history in the US. And what we looked at specifically were landfalling hurricanes striking the United States. And that's because it is possible in sort of early 1900s, we might have missed a hurricane that was out to sea and nobody knew about it before we had satellites monitoring the surface of the earth and monitoring the weather. But it's very hard to miss a hurricane that makes landfall. And so we're very confident about this time series. And if we have a look at this time series, it turns out that it's neither significantly increasing, as the media might sometimes suggest, nor is it significantly decreasing, as some of the models suggest. But hurricanes are so rare that it might be actually really hard to see any signal in this time series yet. But it's important to know that there's no trend yet. Some people wonder whether just the most intense hurricanes have gotten more common. There's no trend in landfalling major hurricanes, category 3 and up. There's no trend. So we can return to Senator Bernie Sanders' quote, "Let us be clear, Hurricane Dorian has everything to do with climate change." We cannot endorse that statement because we don't know how climate change is affecting the number of hurricanes. So I've talked about heavy precipitation, some of the most intense precipitation. We can also understand how climate change is affecting the other side of the coin, that is drought conditions and evaporation. So here I'm showing two dry sponges, dry air, and they're evaporating up water from the surface, from the soil. And if you have a bigger sponge, then you can absorb that water more quickly. And so for that reason, we understand that evaporation into dry air has intensified with warming. And we think that this could be an ingredient in exacerbating some droughts. For the same reason, this intensified evaporation could also exacerbate wildfires because evaporation into the air is how the fuel for wildfires, the plant matter, can get dried out. But again, for these four phenomena that I discussed, hurricanes, heavy precipitation, droughts, and wildfires, it is true of all of them, just as it was for hurricanes, that we don't have a comprehensive understanding of how climate change is going to affect the number of these events. And we especially don't understand how climate change is affecting the number of these events at a regional level. So you want to know what is happening to me now as relates to these four events. Climate science cannot yet confidently provide that information. We would like to be able to, but we cannot provide that information. And so we position these four impacts on the boundary between settled and unsettled. We have physical insights and understanding of how climate change might exacerbate a given one of these events, but we don't know how the overall number is changing, and we don't have regional level insights. What we do have confidence in, sorry for the screen being partially blocked, we do have confidence that heat waves have gotten worse, as I explained, sea level rise, and water vapor increases. Those are in the settled portion. And once you're done playing with that, so this does conclude my section on looking back at the past impacts of climate change. And so now we'll pivot to looking ahead to what the future holds. Dr. Jake Seeley.
All right, hi everyone. I'm Jake. Let's see. I'm from the Midwest. I grew up with views like this in my backyard and just sort of naturally fell in love with thunderstorms, and went to UC Berkeley to get a PhD to understand how these storms are changing as the planet warms up. And I've now moved to Harvard in Massachusetts, where I'm a scientist there. Okay. So we're going to be talking about the future now. And just to refresh your memory, we've seen already that climate change due to our past emissions has warmed the planet by around 2 degrees Fahrenheit. And the question now is, what is this temperature curve going to look like going forward, 50, 100, or even 1,000 years into the future? So to get the gears moving on this, I want to pose a thought experiment to you, which is the following. If we stopped emitting carbon dioxide tomorrow, imagine we could just snap our fingers and magically shut off every power plant burning fossil fuels. Would the temperature increase, stay the same, or decrease? So graphically, that looks like this. Here we are in the early 21st century. Imagine, just for this thought experiment, that our emissions stopped on a dime tomorrow. Would the temperature then continue to increase? That's path A. B, stay the same, or C, quickly revert back to the pre-industrial temperature. So think about which of these seems right to you for just a moment, and then I'll actually take a quick informal poll. So think about what sounds right to you based on things you've heard about warming in the pipeline or the biosphere taking care of this problem. Are you ready? Who thinks it's A? Temperature continues to increase. See about 4 votes there. B, stay the same, maybe 5 or 6, and C, decrease. About 5 again. That's pretty even. So, ding, ding, ding. Correct answer is choice B. Temperatures are constant after emissions stop, and this is something that we've really only realized in the past about decade. And they're not just constant for 50 or 100 years. They're constant. Remember, this axis goes all the way out to year 3000. So it's 1,000 years into the future that temperatures are constant. And that's really remarkable. I mean, we do not know what the world will be like in the year 3000, but climate science says that if we stopped emitting today, they would have our climate, even 1,000 years in the future. Of course, we cannot stop emitting on a dime, and so it's very likely that we're going to continue to warm the planet. There are various targets that the international community have agreed upon, and the most famous is this Paris target, which is to limit global warming to below 2 degrees Celsius, about 4 degrees Fahrenheit. So if we pulled together and did that by around 2100, which means stopping emitting fossil fuels by 2100, when the temperature rises around 4 degrees, that's the climate that we're going to have for generations and generations and generations, a 4 degree Fahrenheit warmer world. But of course, that is also not a sure thing. We could take a couple centuries of continuing to burn fossil fuels. We could raise the temperature of the planet by 8 degrees Fahrenheit. But if in the end we ultimately decide to stop burning fossil fuels, we're going to get stuck with an 8 degree Fahrenheit warmer world for basically ever, for civilizational timescales. So there's really 2 ways to look at this. There's sort of an optimistic message, which is that the future is still up to us. Because future warming is caused by future emissions. If we stopped emitting today, the temperature would stay where it is. So we have to continue burning fossil fuels for things to keep getting worse in terms of temperature. So I take some hope in that. We're still in the driver's seat. On the other hand, the fact that these temperature curves are flat for 1,000 years really means that global warming is permanent on a very long time scale, and it's irreversible. So when we stop emitting, that's not when the problem gets better, it's when it stops getting worse. All right, so given that our emissions are the most important determinant of future climate, we have to put in assumptions about how much future emissions humans make in order to project the future climate. So I want to compare 2 scenarios for you. One is what we'll call extensive climate action, where we try to meet that Paris target of limiting warming to below 4 degrees Fahrenheit. And the other is what we'll call an unabated emissions scenario, where our fossil fuel use continues to grow with population over the 21st century. And that's about 8 degrees Fahrenheit warmer on average by the year 2100. So these two maps are the average temperature change in those two scenarios. And I hope you can see that there's a lot of spatial variability here below the average. There's two patterns that are known. One is that land tends to warm faster than the global mean, faster than the ocean, about 1.5 times as fast. So land in this 4 degree Fahrenheit world is more like 5 or 6 degrees warmer. The other pattern is that the high latitudes, the Arctic and the Antarctic, they tend to warm much faster than the tropics. So some of the high latitude land in this unabated emissions is warming more like 12 or 15 degrees Fahrenheit. So you would really feel that. Parts of the country that currently have a decent winter with a ski season could lose that ski season entirely. And places that have heat waves in the summer of 100 degrees could be 115 or 120 degrees Fahrenheit. So that's going to be potentially deadly if you don't have air conditioning or other ways to deal with that. All right, so I want to come back to this schematic of climate knowledge now and talk about a few more impacts that are in this sort of settled side going forward. So it's heat waves and gradual sea level rise. So we feel confident in saying that under unabated emissions, heat waves will become much more frequent, particularly something that happens every 20 years today. A heat wave that's once in a 20-year event will become something that happens every other year by the year 2100. So another way of saying that is that if you have grandchildren that are alive at the end of this century, they would experience really the hottest temperatures that we can remember almost every year. So our extremes become their norm. In terms of sea level rise, we've already seen around 8 inches, 3/4 of a foot. These two emission scenarios correspond to, by the year 2100, about 2 feet and 3 feet total of sea level rise. And that comes from continued melting of the land ice and thermal expansion. But up in the corner there, there's also an additional wedge of sea level rise going up to around 6 feet by 2100. And that's got a question mark, and it has to do with ice sheet instabilities. So what are those? Well, the ice sheets are the big mile-thick sheets of ice on Antarctica and Greenland. And the scientists who study these are trying to figure out how these things melt. We've suddenly raised the temperature of the planet. And there's really two possibilities there. One is these ice sheets melt like an ice cube on your sidewalk, where they just sort of slowly shrink. That's what they are already doing, and that's the sort of slow sea level rise that was in those 2 or 3 foot estimates. But there's another way that they could melt, which is it could shatter. Like you drop a glass plate and it just breaks into a bunch of pieces. The ice sheet could do that and flood the ocean with icebergs, and that would very quickly raise sea level rise over the next century. So deciding between those two outcomes is something that scientists are working very hard on. It's a really hard problem, which we haven't come to an agreement on yet. So that's an example of a tipping point. And if this happened, it would be really catastrophic. 6 feet of sea level rise is going to be really catastrophic for a lot of low-lying areas. Now, the IPCC has some good news on this front. It actually says, this is the consensus statement on climate science, it says it's exceptionally unlikely that either Greenland or West Antarctic ice sheet will suffer near complete disintegration by the year 2100. And that's a statement that we have high confidence in. So really the consensus right now is that it's much more likely for those ice sheets to slowly recede than to disintegrate very rapidly. Another example of a tipping point is permafrost thaw. So permafrost is frozen soil in high latitudes. And there's a lot of organic matter in those frozen soils. And as they thaw, that organic matter starts to decompose, and it can release carbon dioxide and methane into the atmosphere. And that's potentially a scary feedback loop, because the warming causes the greenhouse gases to leach out of the ground, and then that causes further warming, and it could just kind of go on its own like that. But the IPCC, again, has some cause for relief here. It states that it's possible that permafrost will become a net source of greenhouse gases, but we have low confidence in that. And one of the reasons that we have low confidence in this statement is that, yes, as the permafrost thaws, it releases carbon, but there are also changes in ecosystems that live there. In particular, the forest is expected to advance towards the poles and replace this little grassy, shrubby stuff. And so that can sequester additional carbon. So figuring out the balance between the sequestration and the release is something that we haven't settled yet. So based on everything I've just said, I want to now come back to this quote from Jonathan Franzen. He said, "It probably makes no difference how badly we overshoot 2 degrees Celsius. Once the point of no return is passed, the world becomes self-transforming. So the picture that Jonathan Franzen is painting here is that there's some threshold around 2 degrees Celsius where if we stay below that, everything is hunky-dory, and if we go above it, then everything goes off the rails and it's out of our control. And as I showed you, that's certainly not the case with temperature. No matter when we stop emitting, whether that's 2 or 4 or 8 degrees, when we stop emitting, it stops getting warmer. So it's not going to become self-transforming in terms of temperature. Maybe Jonathan Franzen is talking about these other tipping points, like the permafrost melt and the ice sheet disintegration, but those things are not settled science at all. So Jonathan Franzen is making it seem like they're definitely going to happen, but the science is still out. So we would actually put ice sheet instabilities and permafrost carbon release way over on the uncertain side. And just zooming out from this diagram a bit, one of the things that we think is contributing to the mixed messaging you're getting in the media is that various actors are scrambling this diagram. And they may be doing that because they have a motive or because they don't know the science that well themselves. But Scott Pruitt wants to take something very settled, like that CO2 increases the average temperature, and put it over here and pretend that scientists are still actively debating it when they're not. On the other hand, Jonathan Franzen is taking these fairly uncertain things that are actively debated and trying to make it seem like they're settled science. So our hope is that by plotting these things, you can sort of parse those messages when you hear them. Okay, so that's the end of my section. I'm going to pass things over to Nather, who's going to translate these 2 emission scenarios into a sort of carbon budget to answer how much can we really emit.
Thanks, Jake. Good afternoon.
Hi.
Hi. I'm Nather Jeevanji. I'm a native Californian, actually, and I got a PhD in physics from UC Berkeley, pictured here. I actually studied theoretical physics for most of my PhD, and there's even an ivory tower here in the background to symbolize how esoteric that pursuit was. But I eventually decided I wanted to study something more down to earth, and I switched my focus to the atmosphere and the study of climate. And I now actually work in Princeton, New Jersey, at a climate modeling center. In fact, the world's first climate modeling center, where we continue to build climate models like the ones whose output we've been discussing and showing you today. All right. So I want to talk about, so we've talked about the impacts of our emissions that we've seen so far and projected out. And so now I want to sort of shift the focus to those emissions themselves. How much do we have left to emit, and where do those emissions come from? I just want to circle back to something that Jake sort of showed, which is that Jake showed you that once we stop emitting, the temperature stays flat. And so if we emit more, it gets warmer. And it turns out that those effects, how much we emit and how much it warms, is proportional. So the temperature change you see is proportional. It's proportional not to our yearly emissions rate, it's proportional to the total amount, our total cumulative emissions over history, the total amount of fossil fuels that we've dug up from deep underground and put into the atmosphere. And so just putting some numbers on it. So on the laser pointer works. Yeah, so on the horizontal axis here, I have our cumulative emissions in gigatons of carbon. A gigaton is just a billion tons, just like a gigabyte on your computer is a billion bytes. So we have gigatons of carbon here, and then the temperature change on the vertical axis. And it turns out that we've emitted about 500 gigatons of carbon so far. And that's giving us a warming of about 1.8 degrees Fahrenheit. And then this Paris target that Jake was talking about, which works out to be about almost 4 degrees Fahrenheit, that's just about double what we have now. And so it would take, that would bring us up to 1,000 gigatons of carbon burned to get there. And so that means that our sort of remaining carbon budget is about 500 gigatons. That's how much we have left to burn to stay consistent with the Paris targets. So what would that look like to stay consistent with that target and only burn 500 gigatons more? So here now we have a chart of our yearly emissions, so gigatons of carbon per year over time. Our actual historical emissions from data is shown in gray, and you can see that right now our yearly emissions rate is something around 10 gigatons per year. And so maybe the first thing to note is that then if we have a carbon budget of 500 gigatons, and we're currently emitting at 10 gigatons per year, then we sort of have on the order of a handful of decades worth of further emissions before we hit this Paris target. The reason I point that out is because you may have heard reports, especially in the last couple of years, that we have 10 or 12 years to turn things around. And that if we don't, we're going to cross some climate cliff. And that was really a sort of intentional or unintentional misread or distortion of what's in some of these government reports. And what that 12 years really refers to is that, so we've got our historical emissions going up to here, and then a scenario consistent with the Paris Accords is this blue curve here, where we ramp down to zero emissions by 2100s, and we emit a total of 500 gigatons more. And what you see is that there's a pretty abrupt change in slope here from the gray curve to the blue curve. Right? Our emissions are still increasing. In America, they're actually roughly flat, but in the developing world, China and India, emissions are still accelerating. And so to go from that to a world where our emissions are decreasing, that's quite a transition. That's quite a shift. And so this 12 years meme that was going around was really describing how quickly we need to make this transition from increasing yearly emissions to decreasing yearly emissions. It wasn't just talking about how long we have until we hit the Paris. All right, so this 10 gigatons a year that we're emitting, where does it come from? Obviously, there's some emissions that we're very familiar with when we flip on a light switch or we drive our cars. But is that really everything? What else is there in this carbon budget and in our yearly emissions? So maybe the first thing to say is that besides fossil fuels, there are other sources of carbon dioxide. In particular, deforestation and other changes of land do emit carbon. So if you cut down a forest to create, say, agricultural land or land for grazing, those trees, when they decay, the carbon that's stored in them when the trees decay is released into the atmosphere. And so that's accounted for here in this part of the pie chart. But what this chart shows is that really the vast majority is really fossil fuels. Again, digging that stuff up from deep underground and burning it and releasing it to the atmosphere. So we can decompose this pie chart a little bit further. There's many ways to slice it up. This is one way. And so 41% of the total electricity and heat. So that's not surprising, right? We're burning fossil fuels in our homes to heat our water, to heat our homes, and then of course all the myriad uses of electricity. And so that's a big piece of the pie. Another maybe perhaps unsurprising piece of the pie is transport. So of course a big part of that are the cars and trucks we drive, but also shipping and airplanes. They also contribute. Perhaps something that's less familiar is manufacturing and construction, 17%. So comparable to what we put in our cars and trucks and for transport. And a way to think about that is that there's various industrial processes in making things that actually require the manufacturers to burn fossil fuels on site. So if you are smelting steel, if you are refining oil, if you are milling paper, right, you need high heat. And so you're going to burn, say, natural gas on site to generate that. You're not using electricity for that. And then, of course, there's heating and cooling our buildings, and then the deforestation and land use, like I mentioned. And so one takeaway from this pie chart is that our carbon dioxide emissions really cut across so many sectors of life. They're pervasive in modern life. And some of these uses are things that we're very familiar with. Of course, we know that when we fill up at the gas station and drive our cars, we're burning fossil fuels. But we're not always thinking about the fossil fuels that are embedded in some of the products that we use, or even in the buildings that we inhabit. So, given the pervasiveness of this, if we want to reduce our emissions, what do? There are solutions out there. For instance, in the electric sector, there's renewable energy, wind and solar. For transport, we've got electric cars that are becoming more and more pervasive and widespread. In manufacturing and construction, there's a solution that's sort of on the table, not yet widely deployed, also applicable to fossil fuel power plants, which is where if you're burning fossil fuels and you've got CO2 coming out of your smokestack, you can actually capture that CO2 with chemicals and then pipe it underground to geological repositories where it's thought to be safe to store it for hundreds of thousands of years. And often these repositories are actually, ironically, old fossil fuel wells, so oil wells, gas wells, and coal beds. And so these solutions are out there. Some of them are, we're seeing more and more of, solar panels and wind turbines, but they all come with trade-offs, right? all these things are expensive, right? Solar farms and wind turbines, those are massive capital projects, right? They require a lot of money up front, as would transforming our vehicle infrastructure such that charging stations replace gas stations, right? That would be a huge effort and a huge expense. And technologies like this, the carbon capture and sequestration that I was talking about, they work, but at present they're too expensive to really be deployed on a wide scale. And so what that means is that the question of solutions, which is a question that of course comes up when talking about climate change, it's hard to talk about climate change and not talk about what we're going to do about it. But as scientists, we do have a privileged perspective when it comes to the science because we spend all day thinking about it. And science is one of the few places where there are such things as hard facts, especially once science is settled, right? But when it comes to the shoulds, what we should do, science doesn't have a privileged perspective on that because the choices we make about what we do with this have to do with our values and our priorities and our beliefs. And those are questions for us as a society to ponder together. And so we hope that the presentation that we've given you here today is really just a springboard for that bigger conversation. We hope to have some of that conversation with you here today and also answer questions about the science. So we'll end here. You can find us on the web at climateupclose.org. If you'd like to support our organization and this type of outreach, you can do so and donate at the website. And with that, we'd be very happy to take your questions and be in conversation. Thank you. So the way we'll do this is we'll actually take several questions all at once without answering them, and we'll write them down and sort of kind of clump them together and figure out what order we want to answer them in, and then we'll go through them all and give answers. All right, so go ahead and raise your hand, and we'll call on people and raise your questions down. Would you mind reading them? Or?
I think Katie's been having.
Okay, awesome. Okay, sure. Yes.
An increase in tornadic activity, is that lumped with hurricane, or is that, where does that fall?
Good
More
question.
settled uncertainty.
Great question.
Yeah, I'm curious about the plateau, the temperature plateau. So that was over like 3,000 years, or 1,000 years horizon, I guess.
Yeah.
So thinking about that, there's conversation about reforesting, there's conversation about direct air capture and investments in level effect and all sorts of things. Over that type of time scale, is that proportional to the task of getting the back out?
Okay. Great question.
Are you aware of, or is there, I read about there's a GIS study going on in climate change that breaks it down into small areas and then combining it? Are you aware of that or know any progress of it?
Are you thinking about any specific aspects of climate change? Temperature or rain or vegetation or?
They were developing a model based on micro areas.
I see.
I read about it several years. They said it'd be 7 years more. But were you aware of it or?
Okay, it's not ringing a bell, but we could talk about how we try to scale things down to the local scale.
Do you have any information on oceans and acidification that's going on and lack of oxygen?
Yeah, thank you for raising that. We didn't touch upon that in the presentation. In the back.
So one of the things that we look at that we're concerned about here is the aquifer levels. And we are concerned with things about like overpumping, removal. So to take all of that into consideration, what would the global warming effects have on aquifer levels?
Good question. You guys are testing us. It's good. We like that.
Why is it not reversible? I understand that you said levels, we stop, it's levels off, but why is it, other than humans, so why is it not reversible?
Great question. Very good question. All right, we could probably take one or two more if they're out there. Don't make me call on you.
We also have some from online, I think.
Are those already in there?
Yeah.
Okay, well, this is plenty. We could
Yes,
start with
that's
this.
great. Yep.
All right, if anyone else starts off.
Sure, there was a question about why are the changes irreversible? And in terms of temperature, why does the temperature stay flat for thousands of years? And the first thing to know is that it took millions of years for basically plants to take up that carbon dioxide and then get deep into the Earth's crust and compactified into coal and into natural gas. So the time scale that took the carbon out of the air, that takes place on the millions of years. That's the longest time scale in the problem. Now the carbon dioxide that we're putting in, first it's going to go into the ocean. It's going to diffuse into the ocean. And here's a little tricky point, which is that it will get taken up. Some of that carbon dioxide will get taken up in the next 100 years, the next 200 years, the next 300 years. So there will be carbon uptake. And from that perspective, there'll be less heating in the system. But somewhat counterintuitively, that doesn't actually decrease the temperature. And that's because there's another effect that's really important. And that second effect is that right now, the surface of Earth is able to cool to the deep ocean, because the deep ocean is very cold and it takes a long time for the ocean to overturn and to see the surface temperature. So the deep ocean is like a heat sink that we're able to cool to. And that's actually been moderating the current temperature. However, you can only dump so much heat in the heat sink until it starts to warm, and then you can't cool to it anymore. So it's the second effect, which is the disappearance of the deep ocean heat sink, which roughly balances the decrease in carbon dioxide from uptake into the ocean. So in some sense, it's like the heating rate goes down and the cooling rate goes down together, such that there's a balance and the temperature actually stays the same. So it's like you turn on a heater in one corner and an air conditioner in the other, and you don't get a change in temperature in the room. So these two counterbalancing effects, the drawdown from CO2 and the disappearance of the heat sink, result in that flatline temperature change. So that was a mouthful. I hope some of that got through, but
That's a very solid answer.
okay.
And Nathaniel's actually studying this as a follow-up to previous climate eclipse events. Nathaniel has active and Nader have active research on these questions. So you heard it from the person who knows it.
Yeah, so the 1,000 year horizon question about what carbon sequestration could do on that timescale, it's related to the same theme. So, since the warming is proportional to the cumulative emissions, that actually applies to negative emissions too. So if you can somehow remove carbon from the atmosphere to get it back to say 500 gigatons of total emitted, 1,000 plus minus 500, you would get back down to the temperature that you got at that cumulative emissions. Now, to capture that much carbon, you're talking about a direct air capture network that's as big as all of the fossil fuel infrastructure that we have now. So like every place that we're burning it, you need to instead be doing a much harder thing, which is finding all of the CO2 molecules in the atmosphere, concentrating them and sequestering them. So it's possible. It would be building a second ride-along infrastructure along with everything we have now. So it's very expensive and would take up a ton of space.
Just want to do that now?
Yeah, how about we? Katie, can we invite you to weigh in on tornadoes?
Sure. I was also thinking that what Nathaniel was just talking about relates directly to the ocean acidification question. Nathaniel, do you want to mention that? Or do you want me to?
Yeah, go for it. Go for the.
Yeah. So what Nathaniel was describing with the ocean acting as a sink for carbon dioxide is exact cause of ocean acidification, because the carbon dioxide, when it gets dissolved into the ocean through some chemical reaction, turns into acid. And that we didn't cover much in this presentation about biological systems or ecosystems. That deserves a whole other presentation. But that is a major concern that will play out over our lifetimes. The one that I'd put my initials next to about increases in tornado activity is a really good question. Obviously, it's been in the news a lot. And most of the news coverage I've seen proposes a direct causative effect of climate change causing tornadoes activities. But if you look at the reports of the International Panel on Climate Change, which is, or Intergovernmental Panel on Climate Change, which is a collaboration across many different countries that does a really thorough job of synthesizing exactly what our knowledge is about the current state of the climate. They present very low confidence in even any trend that's being detected, much less any attribution of that trend to climate change. So we don't even have a confident statement about whether tornado activity is increasing or decreasing up to this point. There's some scientific studies that have been done on a smaller scale that actually suggest that the incident rate of tornadoes in the future as warming increases will decrease, but the tornadoes themselves will get stronger. That isn't necessarily like a high confidence statement on the part of the entire climate science community. It's an area of active research, so it would be in kind of like the unsettled part of our map.
Perfect. I'll take the next question. I think this one might have been submitted in the chat. What steps can be taken to have meaningful impact to reduce carbon emissions in developing nations? That might have been here in the room, actually. I don't remember. That's a great question. It's a hard question. It's not one that we have a privileged perspective on. And the climate change problem pushes people to balance their humanism on the one side of wanting to see everybody have a chance to better themselves and go through the industrialization that has already occurred in the US, and balancing it against also caring for the environment and caring for future humans. So humans today, humans in the future. These are values questions. The industrialization in the US is in the past. There are many, many people for whom their industrialization is potentially in the future. If they go through industrialization the same way we did, that will add a lot of emissions. They don't have to go through industrialization the same way we did, because we have already done it, and we have technologies that might help them industrialize potentially in a cleaner way. What could that look like? That could look like technology transfer, sharing of patents. There are people who think way harder about this and have way more grounds for talking about these issues. But I think there's a chance that the world could be made better for people still developing through some of the wealth of ideas and resources that has been gathered already in the developing world. That's an option that the developed and developing world has to interact.
Great. Maybe I'll take a question about the impact of food production in generating greenhouse gases. Where was that? It's something we talked about. So it was sort of in the land use change part of the pie. So I had one pie chart that showed land use change was something like 17%, 16%, and fossil fuels was 84. And within land use is deforestation for agricultural or pasturing purposes, and so that's part of the emissions associated with food production. But I think that question may have come from online, right? But another aspect that you may hear a lot about is methane emissions, and so that's cows emit methane, also manure from animals emits methane, and And so that's something that if you accounting for that can increase that share of the pie. The tricky thing is that methane actually, unlike carbon dioxide, which is Nathaniel was just discussing, once it's in the atmosphere, it takes a long time for natural processes to kind of sequester it back underground. Methane actually decays to other gases very quickly, relatively quickly, on a time scale of say something like 10 years. And so, but it also turns out that methane, molecule for molecule, is actually a more powerful greenhouse gas than carbon dioxide. So there's this, if you're going to try to equate methane emissions with carbon dioxide emissions, it's quite tricky because on the one hand, it's more powerful, but it doesn't last as long. And so the way people often do it is they just choose some time scales, say 100 years, and say, okay, if we just average over 100 years, then we can compare the contributions of the two molecules. What we chose, but as you've seen, carbon dioxide is special because it lasts hundreds of years to thousands of years. And on those time scales, any methane that a cow burps up is long gone. And so it becomes difficult to compare those things, especially when you want to think about the long term. So we made a choice to separate out the contributions from methane and really focus on carbon dioxide. But it raises an interesting question, right? If what you're most concerned about is like really short-term, near-term warming, then you really do care about that methane. But if you're really thinking about the long term, then CO2 is the most important.
There's a question here about what's the net improvement of electricity usage versus reduction of fossil fuels, mainly for electric cars. And one idea I wanted to get out there is that your electric car is only as clean as the fuels you use to charge it. So if the fuels you're using are coming from a power grid that's based entirely on fossil fuels, well then in some sense you're responsible for those fossil fuel emissions, just like you would be if you filled up your car in gas.
But I think it is about twice as efficient even so.
Okay.
Per mile, but it's still dirty.
Yeah, the calculation I'm familiar with is that if you're filling up your car with mainly a power grid that doesn't have much renewable energy in it, then it'd actually be better to not have bought the Tesla or the new car, because associated with making that car is a bunch of industrial emissions. So if you have your old, beat up truck, you can actually lower your emissions given the current energy infrastructure by just continuing to drive it. But if that energy infrastructure changes and it becomes based on renewables, then obviously the calculation is different.
Yeah, so there's a question about aquifers. How would warming influence aquifers? So I think there's not one answer to that question. So I mean, in general, the groundwater level is going to be a function of the local balance between precipitation and evaporation. And in some places, that balance is going to change towards the side of drought. And in some places, it's going to change towards the side of more water. So in some places, like in California, they're very dependent on the snowpack that happens in the winter. They get a huge pack of snow in Sierra Nevada, and then that runs off in the spring and is stored in aquifers. So there we can say pretty confidently that if it gets warm enough, they'll lose that snowpack. They won't have that runoff in the spring, and their aquifers will be in trouble. In terms of Florida in particular, I'm not sure about the local result. I think those sort of like local changes are an example of the things that are very uncertain because it's so small scale. And there's no clear sort of mountain story that you can tell here.
Actually, the big problem here in Florida is saltwater intrusion into the aquifer.
So
it's statewide.
Gotcha. So that's not a global warming effect directly, it's a sea level rise, saltwater intrusion. Yes.
We're experiencing that now with saltwater intrusion. If you're familiar with the area, it's up to and past Highway 98, just south of here in the cave system. When you go into the cave system, there's 4 different layers. You've got salt water, brackish water, and you've got hydrogen sulfide and freshwater layers come in through the cave system, and the cave systems are massive, 50 to 100 feet in diameter, and a lot of volume there. So we're already experiencing, because of sea level rise, or we assume it's because of sea level rise, that saltwater intrusion here that we just talked about.
Yeah, that's a great point, because a lot of times when people estimate who's going to be affected by sea level rise, they do something simple and they just take the topography, you know, the contour, and say, well, where would a sea level rise of 6 feet intersect? But as you're pointing out, even underground, there can be effects of sea level rise much further inland because of the infiltration. It's a great point.
I'll weigh in on this question. We were asked about a GIS study on sort of micro zoomed in areas. It's a good question. It's not a specific study we're familiar with, but I'm going to just offer some intuition about the tools that climate scientists use to look at different scales. So the climate models that we introduced in the talk and that we use to talk about global warming, it's a computer model of the whole Earth, and it kind of breaks the atmosphere up into little boxes, and it breaks the ocean up into little boxes and sees and studies how the air and energy flows between them. And to do that, you have to have a certain size of the box. And the best climate models we have today, those boxes might be around 100 miles long by 100 miles long, and maybe half a mile deep or something like that. And you kind of stack them up and make a 3D grid of the atmosphere. And that means these models can say things about what's happening at these very large scales, like the global warming. But it's also why these models might struggle to say something about, for example, tornadoes, which we talked about. The tornadoes are not even in the climate model. And so we can't say something about how these global effects might influence tornadoes. Now, what you can do is you can make a new model, which is a smaller box. Maybe it just represents the state of Oklahoma. And then you can take all that resolution and cram it in, and then maybe you can represent a tornado. But now you just have a model of the state of Oklahoma, and you don't have a globe anymore. And so then it's hard to say how the global factors are changing. And so part of the challenge of climate science is how to make statements that involve small scale phenomena and large scale phenomena at the same time, and how they're interacting across scales.
Looks like we had a question maybe online about what's the difference between buildings and heat. So I think that's referring to the pie chart I showed you, which had electricity and heat in one spot and then buildings in another. I have to confess that I need to look into this to figure out exactly what the difference is, but I think part of it is that so for buildings, that's just the heating and cooling of buildings.
Burned inside the building, like a natural gas heater within the building.
That's right. But we use natural gas inside our buildings for other things, for instance, for cooking and also to heat water. And so I think in the pie chart that we have, those end up being split up into different pieces. I don't know if anyone amongst us has seen Drawdown or can...
Can we invite Katie? It looks like she has bolded one.
Right, did we get to that question already then?
Maybe she added that after I answered it.
Okay, well, yeah, should we
add?
Yeah, should we hear what she has to say?
Katie, did you add, weighing in on the 1,000 year, would you like to add something about that?
Yeah. Did I miss it? Did someone else already talk about this? Sorry.
Can we?
Did someone else already answer this question?
Yeah, a couple of us have taken a hack at it.
Okay, I'm sorry.
That's fine. I wasn't sure if you had something to add. I wanted to invite you, so. But yeah, we discussed it a little bit.
Maybe this is a good point to wrap it, and we'll be here, all four of us, to continue the conversation.
If we didn't get to your question, then we have to talk a little more.
Can I ask a quick last one?
Sure, go for it.
I think, if I'm correct, you said there was, at the moment, no significant correlation that had been made between global warming and intensification of hurricanes, right? I think
that's right. Yep.
Now, when the hurricane adverbs over the ocean, if there's a warming of the sea surface temperature of the ocean, you increase the availability of potential temperature for the hurricane, right? So
that's
you directly imply that there will be a potential for intensification of the hurricane. And so I was a little confused by the argument that you made that we could not so far construct correlation between global warming and intensification of hurricanes. I was a little confused by your argument.
Yeah.
Well, just to be clear about what we're saying.
Can you repeat the question for the Zoom?
Sure. A member of the audience asked a question about how the effect of having a warmer sea surface potentially intensifies the hurricane, and how that contrasts with what we were saying, and whether there is a point of difference there. So the first bit I just want to make clear is that we do think that precipitation has intensified, and that is linked to the fact that the air is warmer and can take up more water. So there is an intensification link. In terms of the wind speeds and the overall power of the hurricane, the challenge is it's not just about the sea surface temperature, it's also about the temperature at the top of the atmosphere. So one can think of the hurricane as like an engine that's running off. It has a hot part and a cool part, and heat is flowing from hot to cold, and that gets turned into the winds. The challenge is that in some places, the top boundary condition is also warming. So both the bottom and the top are warming together, and the hurricane can really only see the difference between those two. So that's a confounding variable that makes it hard to say whether the hurricane is going to intensify on its own.
The intensification of hurricanes is a very active area of research, and it's actually one where the differences among scientists can be sort of comparable to the differences among what people really want to know in the public. And so there are, scientists we know put their heads together and try to think of the best consensus statement they could make on intensification of hurricanes. And what they came up with is hurricanes might be getting more intense. And so in our main talk, we try to focus on high confidence results, but we also want to trust you. Okay, so now you know, hurricanes might be getting more intense. And we thank you for your question. Yeah.
I would just add that that's one of those things where, because of exactly the argument that you made, that the sea surface temperatures are getting warmer, and so we expect there to be, sort of more fuel for the hurricane. We do sort of expect to see that in the future. And there are some climate modeling results that bear that out. But when we look at the observed record, and Aaron showed a plot of that, at least in terms of landfalling hurricanes, because hurricanes are so rare,
Which is
right?
only a minority.
It's a minority, but even if you, right, so then people have looked at this, so then you can try and look at all hurricanes, but then there's sampling changes over the years, because more recently we can observe hurricanes, through satellites and other means, whereas 100 years ago, if a hurricane happened over the Atlantic or the Pacific, we would only know it if a ship passed by. So there are changes in our observing networks. So the data that we have is inconclusive on trends in hurricanes. So even if we expect to see something down the line from what the models tell us, that can be true, but it can be hard to say something about what we've observed just because of the nature of the data and because the events are rare. All right, well, I think that's it for the sort of public Q&A, but we're happy to hang out and mingle and talk to you and hear from you all. Thank you.
That's right. And we might step outside because it's so beautiful out.
Yes, let's mingle
I asked
outside.
a question about the recording.
And someone at home said, thank you for an honest, balanced presentation, allowing for a powerful discussion. I think that was very
Yes.
succinct and well put.
Yes, and just what we're going for.
I sent a question. Amy, I sent a question to you about the recording. Did you get it? Amy?
Laura, I could ask, are you wondering if the recording will be available? I'll see if Nathaniel can get an answer.
Amy was trying to get a question answered for me about the recording being available.
Yeah, I was trying to call Nathaniel, who is one of the presenters,
Okay.
but I'm not sure if that's coming through on his end. If you, oh, hello. Hey, one of the Zoom participants wanted to know if the recording will be available.
I'm not sure.
Okay.
I can ask.
Yeah.
Okay. Give me 1 second. I'll go and ask.
Okay.
So, are you there, Katie?
Yeah.
Okay, so